Hello, I'm Tim Holey from Washington University in St. Louis, and this is the first performance lecture in the course Advanced Scientific Computing, Producing Better Code. Today we're going to be going over some of the features that Julia offers for producing high-performance code. So one of the most attractive things about Julia is the really exceptional performance you can get by writing code in Julia. It attracts many new developers to the language. And Julia really does make it possible to write code of the highest performance. I'm not aware of circumstances in which I can't match the performance of fast languages like C and Fortran using Julia. However, Julia does not guarantee that all code ever written in Julia is performant. In particular, you can get performance that is much slower. In some cases, it's even possible to write code that's slower than languages like Python, MATLAB, or R if the implementation doesn't leverage Julia effectively. And there are really two aspects to this. One aspect is, of course, you can choose a bad way to solve a problem. That's always a possibility. And we'll be covering that in a different lecture. Today, we'll actually be talking about particular characteristics of Julia that make it possible to get really high performance code, but then illustrate some of the ways in which you can essentially break those mechanisms and make it impossible for Julia to generate high performance code. So early on in this course, I distinguished truly fast, meaning things that pull all the tricks in the book in terms of different types of hardware optimizations, from code that simply isn't slow. And today, our goal is to avoid, it is not to seek the highest performance code, but simply to avoid having Julia be slow under many circumstances. So the good news is that Julia really does have good tools for diagnosing when things go wrong. And that's really the main focus of today's lecture, is to walk you through some of these tools and the concepts that underlie them and the reasons why performance can degrade in some circumstances, so that you can solve these problems. And the most important tool, of course, in all of these circumstances is your own mind, thinking about the code, thinking about causes, etc. But if these tools really help you collect the data that will allow you to effectively reason about these types of problems. So today, this is really in some ways going to be a deeper dive into Julia's inner workings, really. So the sort of centerpiece of today's lecture is going to be on type inference. We mentioned this early on in the course. We're going to take a much deeper dive into that today. We're going to talk about Julia's methods and specialization, the different flavors of dispatch, meaning the selection of which method is applicable to each particular call, runtime versus compile time. And then I'm going to illustrate two other operations that can help you collect data, benchmarking and profiling. I do warn you that this can be a little bit complicated. It's gotten a lot easier in recent time, but learning these tools really will help you accelerate your progress. So investing in yourself to learn to use these tools effectively will pay dividends in terms of your ability to write high performance code. So we're going to start with a really, really simple example. And it's so simple it will seem very trivial, but doing it carefully will allow us to really analyze how Julia works carefully. So what I'm going to do is I'm going to define a function, just add two, and all it does is add two numbers together, about as trivial as it can get. One of the things you'll notice is that Julia prints the fact that it's a generic function, which means it's a function that you can add additional methods to, for example. It's written in terms of other functions in Julia. And there's exactly currently one method associated with this generic function. And so if we call this method, here I'm going to call it with two floating point numbers. And what you can see is, sure enough, you get the expected answer 3. Now, one of the things that's worth noting is that I can also call this not with floating point numbers, but with integers. And the thing I want you to notice there is that when I call it that way, I get 3 back also. These two numbers are, of course, mathematically equivalent, but they're very different in terms of their representation in bits in the actual computer hardware itself. And so what you can see is that this, when passed different types of inputs, the return type is also different. So it's worth asking yourself, how does that actually happen? So first of all, did Julia create some additional methods behind our back? And so we can ask Julia that question. So here we're going to ask it how many methods there are, and it still insists there's really just one method, and it will give the sort of line number because this is a Jupyter notebook. It'll use this sort of notation here. But if you had if this were code in a file, it would tell you, the exact file name and line number. We can ask we can ask which method is being used to carry out a particular operation with the @which macro, and I'm going to store this in a variable m here. So the m is going to be a method, and so here you can see the printing of that method here, basically. Now, there's a package that you can use to take a deeper dive into methods and the code that gets generated from those methods called method analysis. And it has a function called method instances, and you can pass several things. You can pass functions and the types of the arguments, or you can pass methods, or you can whole modules. It's a very flexible command. Here we're just going to ask what are the so-called method instances attached to M. So I'll show you what a method instance actually is. So the thing to notice about the printing of a method signature is it mirrors what we typed. When we defined the add_to function, we didn't insist, go back here, on any particular types for the inputs. Basically, anything that supports the plus operation is an acceptable input. Here now, when we call method instances on it, what you can see is that it returns a vector of method instances, and there are two of them. And what you can see is that these two method instances here match the two types of calls we've already executed, right? So here we executed it for two floating point numbers. Here we executed it for two integers. And these method instances, these exactly match the list of method instances here. Now, we did not manually create these method instances. Instead, what happened is Julia created them. These are, again, the name is evocative, instances of a method. It's a single method. The method is what you write as the programmer, and the compiler creates these method instances. And so this is an example of what I would call compiler specialization. I would distinguish that from user specialization, meaning we could write a different a method that works by a different principle for add_to past specific types of things. Like if you wanted to pass in two strings and have it, I don't know exactly what add_to would do in that circumstance, but it might do something that's quite different for those types of inputs. That's a user level of specialization, meaning you're creating new methods that for the same underlying add_to function. But in this case, this is something the compiler is automatically doing whenever it needs to run code for different types of argument inputs. So we can force Julia. So you notice there were two so far. We could force Julia to compile yet another version, or yet another method instance by calling it with a combination of argument types that we've never used before. So here I'm going to pass in an int and a float 64. And so we'll execute that. What you can see is you get the float back, and that's because Julia, when it is asked to add an int and a floating point number, it does something called promotion, where it promotes the int into a floating point number and then adds them together. And so now we can ask how many instances are there. It's the same one. Here now you can see that we have three specializations of this method here. So there's the two with the two floating point numbers, the two ints, and then here you can see that this is the one for the int as the first argument and a floating point number for the second one. So again, there you saw right before your eyes the creation of yet another method instance. So Julia creates these method instances the first time that you call add_to with a given set of types. So if you pass in a novel types, before it can execute your code, it has to generate another method instance and compile it for these types of inputs. And then on later calls, because compilation is actually a slow, expensive process, it's very important that Julia saves all that code that gets generated. And so on later calls, it can just use the code that it's already compiled. Now, what are the differences between these method instances? Well, Julia also offers tools for sort of peering into them to see how these actually work. And while I'm illustrating this here in my notebook, the best tools for inspecting this are, I think, actually interactive and require a full REPL, not available in the Jupyter Notebook. So what I'm going to do is I'm going to switch over here into a VS Code window. I started a Julia terminal within VS Code. And I've made just the terminal portion essentially full screen so that you can see things pretty easily. So in this one, I'm going to say using this package called Cthulhu. It's intended to evoke a deep dive into the internals of Julia, and you'll see what that looks like shortly. We have to, since this is a separate Julia session, I have to define my function again. A plus B, okay. And so now I'm going to say descend, add to of, let's start with this one. And what you can see is that the descend macro, when you pass in this call here, what it's doing is it's printing a summary of the method for you. Here it's showing the source code. So the line numbers in the left-hand column, so line 1 of this entry in the REPL, you can see here we defined it in the REPL. What you can see here is now in cyan, it's annotated the types of the arguments. So this is telling us that we passed in 2 floating point numbers, sure enough. This is telling you that it returns a floating point number also. And then on the right-hand side, and if it were a longer function on the lines below, you can see type annotations applied to the individual variables. So here it's saying, in this case, redundant information here, but if you've got a long source code with propagation of information and new variable names being created and all this kind of stuff, these types will tell you what each variable's type is at every stage of your code here. And then what you can see is below the printing of the source code here, there's a set of menus or set of options. And maybe some of the most important of these are toggles. So we're showing type annotations. So you can see this T is in cyan. If I hit T, it will reprint this information, but not show the type annotation. So here you can just see the raw source code. I'm going to go back to the type annotations here. There's a more nuanced version of suppressing all type annotations, which is you can hide all of the so-called type stable statements. We'll see more about that in a minute, but basically anything that's type stable is often used as a term in Julia for meaning whenever Julia can infer a concrete type for an object. So float64 is such an example. It's an exact type. There's only one of that type in all of Julia. So Julia knows precisely what this A object is. And so if I hit H, it looks a lot like suppressing all type annotations, because in this case, all types are concrete in the standard Julia lingo. And so we're not seeing any of those. So I'm going to go back to not hiding the type annotations so that we can see them here. There are several other options. Some of these are kind of intended more for more sophisticated views where you can take a deeper dive into the internals. We're not going to go over those in any way today. The final thing here below here is a list of all of the calls made by your code. What functions did they call? Well, plus is a function. It's represented as it's an infix function in this case, or at least the way we're using it, meaning that here's the function name and the first argument is A and the second argument is B. You can write it as plus with parentheses and you pass in A and B. In this case, though, it's written in the more standard mathematical notation. And if we had made many calls in our code, this would be a much longer list, and we would select using this dot and the up and down arrows on our keyboard which of these calls we wanted to take a closer look at. So, and then this is a back arrow, much like going backward on your browser, basically. So we can dive into, now this is the really nice interactive part about Cthulhu, we can dive into the implementation of plus for 2 floating point numbers just by selecting it with enter on the keyboard. And now what you can see is that we're no longer in our code, which was defined here in the REPL. Instead, we're in a plus method that is defined for specific types. You can see it's applicable to float 16 numbers, float 32 numbers, and float 64. It's in Julia's internal source code. See, here's Julia, the base library, so to speak, and in a file, float.jl at this particular line. We could click on this and actually inspect the source code there, but Cthulhu's printing it right here, so we don't really need to do that. And here you can see the full text of this method here. And what you can see is on the right-hand side, there's a call add float, right? So it's essentially just saying, in this particular case, plus is dispatching, as it's called, to another function that's called add float. And then now we see the same menu below. But in this case, we can't descend any further. Why is that? Well, it turns out that Julia is built on a list of order 100 or so very, very low level primitives. Many of these primitives are just essentially manipulating bits, basically, right? And add float is one of those primitives. So you can't go any farther down than add float. That's the end of the sequence there, basically. But what we've seen is that when you take the plus method, which is a generic function for which there are many methods, then it dispatches to this hardwired method, so to speak, that actually carries out the bit level manipulations needed to add floating point numbers, of course, using the floating point unit of the CPU. So we can go back, in this case, back up to our add to method here, and we can exit just by either selecting the back arrow or hitting Q, okay? Now, that was when we descended with floating point numbers. Let's just take a look at the same source code if we go in with ints. And you can see that basically everything looks the same, except now all the types are annotated as ints. So Cthulhu is showing you what Julia understands about the types of all the variables in the source code, depending upon which types you're passing in as arguments. And we can dive in again to plus implemented on ints, and you might guess, sure, it's not going to call add float, and that you're exactly right. Now it's calling a method for plus that's applicable to various integer subtypes. And what you can see is that's calling a built-in low-level hardwired function add int. And that too is the end of the call chain, basically. Okay, so we've seen how this works in this particular case. Let's do one more example. Let's do mixed type. So we're going to pass an int in as the first argument and a float 64 as the second. And what you can see here again, Julia is showing you that sure enough, it's kept track of all the types correctly. The interesting thing will be when we dive in, what happens. And so now what you can see is we're in a file called promotion. It's a method that's applicable to any pair of numbers. This is essentially what's called a fallback dispatch, meaning if a more specific method of plus is not available, meaning where you noticed here when we went into plus for the ints, it insisted that both of them are in fact the same type of integer. And likewise, when I'm scrolling upward here, if it's hard to follow what I'm doing, here in this method of plus, it was when both the x and y were of the same type of floating point number of abstract float. In this particular case, there's no particular requirement that x and y must be of the same type, right? This is how do you handle a case of heterogeneous input types? And so here you can see it's accepting any kind of number. It's specifically in this case an int 64, whereas y in this case is specifically a float 64. And it's calling this function promote, whose whole job it is to promote to a consistent set of types. And what you can see here is that the promote call returns a tuple, meaning what it does is it takes two arguments in and returns two arguments, where now both of them have been converted into float 64s. We could take a look and see how that might be implemented, and we're diving now further into the promotion machinery. Here you can see it's calling a lower level promote function, and then I happen to just simply know, but you could discover this just by diving into it, that this is something that will throw an error if the promotion didn't really work. So anyway, because that's the nice thing here about Cthulhu is it allows you to really explore at a type level how all of these different methods are implemented, in much the way that a stepping debugger might actually help you see that with values. Okay, so Cthulhu is really great, I think, for helping you visualize the different types that variables have in your code and which methods get selected then to make calls. And so let me go forward. here. So what we've seen hints now of how Julia builds code, and just to sort of make that more explicit, first of all, what you write as a programmer, of course, are text files, raw text, and the strings that are in your files, they get parsed into an internal structure called an expr, stands for an expression, and this is essentially a structure for working with code. It basically will do things. For instance, a simple example is just parenthesis matching, right? So that you can separate out the function calls and get a list of the arguments that are being supplied, et cetera. These expressions undergo an operation called lowering, which basically converts them to a simplified standardized internal representation, the so-called abstract syntax tree. Again, we're not going to really go into the details here in the course, but Julia actually lets you get access to all of these representations of your code if you are curious. You can look up the @code, lowered, et cetera, family of macros. And then all of this is actually done essentially when Julia processes the text files in a package, for example. From there, a lot of what happens next depends on you actually calling the code with specific argument types. And one of the reasons why is because, as you've seen, it's possible to write very generic Julia functions which don't care very much about which types, or which are very flexible about which types you pass into them. Up through lowering, that's perfectly lowering is agnostic about types. It doesn't really care what the types are. It's just generating a representation of your code that's easier for the compiler to reason about. Everything thereafter depends upon the types of arguments that you pass in. So if you call a function with specific arguments, the first step is, if possible, the native code gets looked up in memory and then run, so that it doesn't have to spend any additional time processing this. But if it's never compiled a version of this function f for these specific arguments types, then it undergoes this process of type inference. Cthulhu is showing you the results of type inference for all the different argument types. The type inferred code gets further optimized by Julia, and then we pass the type inferred optimized code off to another compiler called LLVM. And LLVM generates the so-called native code, the actual code that runs on our specific CPU on our particular machine. And then once all of this compilation is done, then Julia will run your compiled code. Okay, so this process can be involved, because you can write high-level code that calls other methods, which call other methods, which call other methods, which call other methods. And so this essentially generates structures that are essentially trees of call chains. The actual operation, of course, might not be a tree, because you can call things higher up on the tree, but at the level of type inference, it essentially becomes a tree. And so the key question the most important, in a sense, decision made by type inference is that once the types are known, Julia can figure out which methods are applicable. So to make this a little bit clear what I mean, you saw an example of this, but to sort of really point out how crucial this whole issue is, let's ask, how many methods does plus have, right? This is how we defined our add2 method, and it called a single method plus on the two arguments. And if we do this, we can see in this particular session, your session may vary, there are 207 plus methods that are defined. In principle, any of them might be applicable. Some of them may be applicable for a different number of arguments than 2. You can throw those out as candidates immediately. But anything else, if you don't know what the types are, you may not be able to exclude them. And so what I want to make sure that you have a mental picture of is that it could take a while to comb through a list of 207 methods and ask which of these apply, and of these that apply, which are the most specific, because that's what Julia's dispatch does. It will say, of all the methods that are applicable, which is the most specific. We may have a plus method defined for number, two number inputs, as we saw, in fact, previously. But if we have one defined for 2 ints and that is applicable, Julia will call the more specific one, the method that's defined for 2 ints, for example. And so So a key point in type inference is to resolve this problem of which method to call at compile time. And so we've seen how all this works. When type inference succeeds, then Julia knows all of the applicable methods and can determine which of them is most specific, and it can make that choice of which method to call during type inference. Okay, so might be called compile time dispatch. Dispatch, again, is the process of choosing which of those 200 or so methods might be applicable, and that dispatch is being performed at compile time. To illustrate this, I'm going to create a little wrapper around our add2 function. I'm going to call it call add2, and I'm going to imagine that there's a list here of arguments I pass in. So it's just going to call add2 with the first item on the list and the second item on the list. Okay. So now let's make a list. So I'll give it another name. Here's a vector of 2 items. This serves as our list. And so if I say descend call add2 of z, now what you can see here is Cthulhu showing you that it knows that list is a vector of int 64. It's showing you that when you extract the first item from the list, it knows that that's an int 64. And when you extract the second item from the list, it knows that's an int 64. And so everything is all fine and wonderful about this thing. We could descend into add2 itself, and here you can see now it looks exactly like what we saw before. Okay, so, but let's do it with a little bit different list here. So I'm going to create this list so that, I mean, we could make this any, that's kind of, let's say, the standard approach here, but just to give something a little more specific, we could, let's say that there are 2 numbers, right? And for reference, let's just say how many methods there are that apply to number of plus, and you can see there's over 35 of these methods that are applicable. They have many different types. We have big ints and big floats and other things like that. So there's still lots and lots of methods that could apply here. And so now let's go descending into call add2 when z is a vector of numbers. Now what you can see is Julia knows that when you extract the first item, it's a number, and the second one is a number. But here, okay, so here what you can see is that, again, it only knows that they're numbers. Now I want to show you another feature of Cthulhu, and that is I can turn on this warn feature. I just hit the W key and it toggled the highlight here. And now you can see that these types are shown in red. Let me just illustrate here for this version. If I turn on the warning and descend in, it's still not shown in red. And in fact, if I say hide type stable, that eliminates all of the type annotations. But if I go back to this number version and do the same thing, so now I'm going to hide type stable and turn on the warning. Here you can see now that Cthulhu's warning you that call list 2 is returning an object of type any, meaning that Julia has no idea what kind of object gets returned by this function. It knows the first number that we extract from the list is the first item we extract from the list is a number, as is the second. But number is not a specific type. It's an abstract type from which there are many specific types of numbers that can be that are subtypes of number. But that doesn't give Julia enough information. And in particular, what you can see is that while there's only one method of add2, so it knows exactly what is going to be called, and it will show us this just as it has before. Now what you can see is that when you look at the source implementation, the calls made by add2, what you can see is that this plus here is annotated with this red runtime. And what that means is that Julia's type inference engine has failed to predict which method of plus is going to be called given these 2 numbers. As we just saw, there's more than 35 possible methods. There's no way for it to predict. If we try to descend into that, I'm going to hit enter with the thing here. And what you can see is Cthulhu will remind you this is a runtime call and you can't descend into it. Type information alone is not enough to resolve the problem. So how does Julia resolve this? Well, When type inference is insufficient, it will essentially pause the execution of your code. It'll ask, okay, but what type of number, or what type of object is A exactly? In this particular case, this moment when we're calling this function, which specific kind of A did we actually get? We know it's a number, but that's not specific enough for us to answer the next question. So we have to pause execution and ask, what specific type of number are you, A? And we have to do the same thing about B. And then what we have to do is we have to look through that list of 35 or more individual plus methods and say which is the most specific applicable method to call, and then call that method, right? And so what that is often called is runtime dispatch. So if we go back here, what you can see is it didn't get very far in optimizing your code. The types have to be analyzed while your code is actually running. And then the really expensive part is picking which method to call, right? If I had made Z a list of numbers, but put in different types, it might have had to call a different plus method than it did for the two ints that I actually placed inside of that list. And so a good mental model for how all this works, I've kind of said this in words, basically, is that when code has already been compiled, you can think of it as sort of a blob of native code. And when you call it, you have to prep the arguments and decide which compiled blob to use. It's kind of like looking up someone's phone number in an old-fashioned phone book, right? And when that decision can be made at compile time, it's quick and easy. It pushes all the variables onto a so-called execution stack, and then it just jumps to the execution of your code. In contrast, if it has to do runtime dispatch, the first question it has to ask is which blob is applicable, basically, for this particular function, and the specific types of arguments that it happens to have for that particular call. Once it's decided which blob to call, then it will prep the arguments, and then it will jump to a site that isn't predictable at compile time, but it will jump. It knows what site to jump to after figuring out which types are applicable. So let's actually compare the output, or compare the performance of compile time dispatch versus runtime dispatch. So here, I'm going to be using a wonderful package called Benchmark Tools. Benchmark Tools contains macros, which are a lot like some of the other macros Julia comes with. So you may know that Julia comes with an @time macro to measure how much time something takes. But when the operation is very fast, @time does not have sufficient precision for that. And that's where Benchmark Tools comes in. And so there's a B time, a benchmark time. And effectively what this does is it will start the timer, and then it will run your code lots and lots of times. And then it will stop the timer and see how long it took, and essentially measure how long an individual call took from having run your code many times. And so what we can do is we can run this run Benchmark Tools here, and you can see with me running Zoom and all, it's actually quite, fairly slow by Julia's typical standards. But nevertheless, you can see it only took just a few nanoseconds here, right? So this is a call, of course, with the promotion of the two types. So we have to convert the int to a floating point number and then add them. If we do this with two floating point numbers, it's a little bit faster. It's a little bit faster, but about the same. And I should say that at B time will give you slightly different results every time you call it. So let's say to start being able to play with a compile time dispatch, we know that we have to hide types from Julia basically, and so Benchmark Tools offers this sort of setup option where you can pass variables into some argument and then use them here. So in this particular case, this is going to create a vector of float 64s, and so that's all okay. And what you can see is that while there's a little bit, actually, I guess that it's essentially the same. It's essentially taking use of the setup information to sort of pre-extract them. What you can see is that again, just the packing them into this vector doesn't really cost us that much. However, what happens if we pack these into a vector of of any element type, right? Where Julia can't predict in advance which plus operation will be needed. And we run this, what you can see is that in fact, in this particular case, it's a much slower operation, right? I mean, this is more than an order of magnitude difference here, right? Now, you might still say, well, 47 nanoseconds, that's not that big of a deal, right? And indeed, if you're doing that once in your code, you will never, ever notice it, and you should never, not at all, worry about that. But if it's something that's on the inside of a loop that runs billions of times, now you're really going to notice something that slows the code down by more than a factor of 10, right? And so it's worth actually keeping these sort of numbers therefore in your mind. If you're doing runtime dispatch, as you've seen here, we've seen something that's on the scale of a couple tens of nanoseconds. It can get slower if you have more complicated calls with more arguments, et cetera. And so it can easily get to 100 nanoseconds or so in complicated case, or even higher than that, basically. And so it's just worth sort of keeping these numbers in mind as you work on code, because it helps you prioritize where to put your effort. And so, but the big thing about runtime dispatch is how much slower it is than compile time dispatch. In my experience, and I think in the experience of many other people, for Julia beginners, it's also a really common problem. So one of the things that happens sometimes is when people turn to Julia, is they translate code that's been written in another programming language into Julia, they run it, they're all excited, say, oh, wow, let's see how fast this is. And it's about as slow as it was in the much slower programming language. And that can be very disappointing, right? But what you should know is that there are some times where that happens simply because in the end, Julia is calling the same libraries that the other code is. If you're doing stuff like matrix, where all the real work is matrix multiplication, that may be the reason for it. But in cases where there's a little more to your code and Julia should be doing more of the actual work itself, then the most likely cause of trouble is that you've got runtime dispatches somewhere in your code. So we're going to talk a little bit more about what kinds of things can be done to detect and eliminate these runtime dispatches from your code. One topic I want to show, and this essentially paves the way for a very nice approach to this problem, and it's also an important elaboration of this distinction that I've set up between compile time and runtime dispatch. And so it's a very informative case to consider. It's called union splitting. So Julia has a union type, which basically means a type is either A or B. Julia may not know precisely which of the two it is, but it's specifically one of a concrete list of types. So in this particular case, I'm creating a union. I'm going to say basically that Z is a list of floating point numbers, and each one of them is either a float 32 or a float 64. This greatly narrows the list of possibilities compared to number or any, right? There's really only two options for X and two options for Y. They don't have to be the same as each other, but those two options are all of the possibilities that there are. And Julia's compiler is sophisticated enough to take advantage of this. We can benchmark this. Well, sorry, here I should do Z of 1, Z of 2. And what you can see here is that it took on the ballpark of 6 nanoseconds or so. It was about twice as slow as the case where it's really just a single operation. Again, we're paying a Zoom penalty here because I'm recording this lecture. But you can see that's dramatically better, than the more than tenfold worsening of the performance due to true runtime dispatch. So how does this work? Well, essentially what happens is it's a hybrid between runtime dispatch and compile time dispatch. It still is in a situation where it has to figure out what the types of the arguments are that you're passing in, but given that the number of options is limited, what Julia can do is it can look up for all possible combinations of those inputs, which are the types that are applicable. So this just shows for a single argument case, if it turns out that one of the arguments is a float 64 or tuple of float 64, it knows it should go run this compiled blob, which basically, again, corresponds to a particular method instance of a particular method. But if the other option is float 64, it can also look that one up ahead of time. So it doesn't say that the query time asking the arguments, what types of objects are you? But what it does do is it saves the method dispatch time, or at least the method lookup time. It doesn't have to comb through a long list of applicable methods, really essentially the list of methods that could be applicable in this particular sort of illustration here are just these two here, right? And so it can check those types very quickly, doesn't have to go look anything up. All the lookup's been done ahead of time at compile time. And so that's why you get performance, which is much, much closer to compile time, even though there is a runtime query of the types of the arguments, right? So you don't in particular need to call this sort of fake function I invented before when talking about runtime dispatch, get blob for arg types. You don't have to go looking up. All that work was done during compilation rather than at runtime. So if you need some type flexibility in your code, and that's very frequent, a lot of very well-written code has this kind of feature to it where it needs some type flexibility. And this union splitting, which basically means handling the specific cases of the union separately, is a nice generic way of getting great performance even in the face of needed type flexibility. Okay, so that is, or maybe I should also show you if I do pass in, let's make this a union float 32, float 64, and let's just see what, oh shoot, that's dumb. Sorry, here, okay. Yes, so I'm making a list in this case of an int or a float 64, and now I'm going to descend, and here I'm going to turn off the hide, or I'm going to hide the type stable ones, and you can see that it's not considered truly type stable. It's still showing me the types, but if I turn on the warn typing, instead of showing me things in red, it's showing me these things in yellow, and that's an indication Cthulhu knows that these are unions of concrete types. So it's unlikely to be a major problem. There's one circumstance in which the union splitting essentially can get overwhelmed. If you have a ton of unions and the combinatorics of the possible number of combinations of types gets to be very large, at a certain point, Julia will stop specializing on every possible combination of all of the different unions coming into a particular method, right? So there are cases where having enough of these unions can cause a more serious form of type inference failure, where things would be printed in red. But for as long as all of these things are in yellow, it's just a note basically to let you know that this is fine code, but if it got sufficiently complicated, it could run into trouble. Okay, so that's all I really need to say about the union splitting. Let me talk a little bit about some of the other tools that Julia has available for you to try to understand how to improve the performance of your code. And probably aside from tools to fix type inference problems, or maybe even more important than those, is a technique called profiling. So if you've programmed in other languages before, it's possible that you've used profilers. If not, this will at least introduce the general concept. What profiling is really intended to do is to allow you to measure where your code spends its time. Okay. Now there are a couple of different flavors of profilers out there. So if you probably the most intuitive form of profiler is called an instrumenting profiler often. And what it does is it adds measurement instrumentation to your source code. So imagine that you've got a function that's running, and this statement is on line 17, and this statement is on line 18. We don't care what these are, just for the purpose of illustration. When you run this under an instrumentation profiler, what essentially happens is that it's actually running code that looks like this. You imagine that there's some internal buffer that the profiler maintains to record data about the execution of your code. It's pushing on information about where you are. So it's telling you, for example, again, this is a fictitious model, but this is sort of mechanistically how you might implement this. It's going to store information about what file you're in, what line number you're on, and the current time at which this execution occurred, right? So this is just going to become a long list of markers where you were in your code at every time a line like this ran. So it would mark that it's starting here at the beginning of this. It might then execute this statement in your code, and then it would take another you sort of snapshot, another mark of where it is in your code, then execute the next line of the code, and so on. Okay. And this is in principle, a very nice, straightforward way of measuring the performance of your code. Unfortunately, these instrumenting profilers actually have some significant disadvantages. The most important one is that they slow down your code. Well, maybe the second most important one is that they slow down your code. That may not be surprising to you because you can see there's extra statements. It has to create, maybe even allocate some space for these profile info objects, and push them, onto into a vector, and then it actually runs your code. So of course, all of these extra statements take some additional time. But there's a much more insidious way in which it can take extra time, and that is the following. Julia and some other languages that have aggressive, highly optimized compilers, the compilers will often essentially rearrange your code to put it into a form that will run at its fastest speed. But a good compiler, a trustworthy compiler, will do that, will make a rearrangement of your code only if it can prove that it has no visible consequences for doing so, other than the speed of the code, meaning that it doesn't change the answers you get, it doesn't, change a region of memory that might be unrelated, et cetera, right? It will only do those kinds of optimizations if they're valid optimizations that have no measurable impact on what your program actually does, right? So the issue is if effectively the way the instrumenting profiler does is it runs code that's been rewritten, and it's being rewritten to push timing information into this buffer before it executes each statement. If the compiler were to rearrange the order of these operations, these timing markers would now be very confused. And a good compiler will analyze the code, which includes, in this case, the instrumentation markers, discover that it would not be valid to rearrange your code, and so it will run the code in the form in which you actually wrote it. What this implies is that well-optimized code, if you're profiling it, may be not as well optimized as it is when it actually runs. And so, in fact, an instrument profiler not only runs the job more slowly than the normal optimized code, it also may effectively lie to you, right? It may tell you that you're spending time in parts of your code that actually turn out not to be relevant in the real code. There are a few other complexities that have to do with recursion and sort of subtracting off the overhead of those timing calls. But I think that those are less fundamental, if you will, than the really fundamental issue that basically you're running different code than the one that would be running without the instrumentation. And so for this reason and a few others, but this is the big one, most of the world, I would say, has switched over to what are called sampling profilers. And these work by a very different principle. They may be much less intuitive initially to you. The idea behind a sampling profiler is that it periodically takes a snapshot of where you are in your code. And to understand this, I want to use an analogy. Imagine that you've tasked a friend with trying to help you figure out how do you actually spend your time, right? So what you've done is you've asked your friend to text you at various times of day, at random times, and just simply say, where are you? And you will respond with your location. And then your friend is going to write it down, or maybe you're doing this for a friend, going to write it down and just keep a log, right? So imagine that, if a person spends, let's say, 8 hours a day at work and an hour a day at the gym, something like that, and there's a friend texting to ask this question, and every time he responds immediately with your actual location, and you do this hundreds of times over the course of a month. You might imagine that over the course of doing this many times, you're going to start developing a picture of where that person spends their time, right? And you don't even have to do that note exactly which particular moment and which sequence these events happen in order to eventually develop statistical evidence that the person spends, approximately 8 times as much time at work as at the gym. Right. So this sort of process of random brief interruptions to ask where you happen to be at the particular moment in time is a way of essentially logging those locations in which you're most likely to be. And if you're spending a lot of time there, that may be a bottleneck in your code, with returning to the actual code, right? And so this is an alternative, a complete alternative. Instead of sort of systematically trying to log every single instruction that gets run, you just do this episodically at random times, and collect statistical evidence about where the time in your code is spent. Now, there are some disadvantages of these sampling profilers, or things that may seem like disadvantages. So one of them is that you don't collect exhaustive information. I mean, in this analogy with your friend, suppose you went to the bank for 5 minutes one day, right? It's pretty unlikely that your friend would text you right while you're there at the bank. And so what that means basically is that's an invisible cost of your time there. Basically, it wouldn't show up in the profiling data, right? But you may not care about that. If you're trying to profile your code and you want to know where the bottlenecks are, you don't care about things that aren't bottlenecks, that aren't accounting for very much of the runtime. You really just want information about the things that cost you a lot of time. Another sort of related issue is, of course, it is subject to sampling noise. Let's say your friend has texted you, gotten responses, that you were at work 100 times over the course of that month. What that means actually is that if you had repeated the experiment, you would get sort of, somewhere you might get, plus or minus 10 counts. So if you have n times that you've observed a particular location in your program, then your uncertainty in the actual number is approximately the square root of that number, basically. And that just comes from sampling statistics. So as long as you know these things about sampling profilers, as long as you don't expect them to give you an identical looking profile each and every time you execute them, then I think they really are the way to go. There are, of course, cases where an instrumenting profiler can be very handy. It's great to have one, and Julia has both instrumenting and sampling profilers, but I think the one that you should reach for as your sort of default go-to is a sampling profiler. And again, with these, you're running unmodified code. This process of interrupting and asking you where you are does not actually require any, there are hardware tricks that can be pulled for that, does not require recompilation of your code in any way. You're running the actual unmodified code when you run a sampling profiler. So what I'm going to illustrate for you now is this sort of process of trying to infer where you are. And I'm going to create a function here called busywait. This is a function that does nothing other than waste time. I could call Julia sleep, but in fact, actually, if you're sleep's a little complicated because it used Julia's so-called task framework and hardware timers and things like that make the interpretation a little bit more complicated. To keep things super simple, I'm just going to create a function that just runs a loop with no actual consequences to it, really, for a certain amount of time. And because Julia's compiler is smart, it might notice that a loop is actually not doing any work. And so in order to prevent Julia from just skipping the entire loop, then what we actually have to do is we have to make it keep track of something and return the value, basically. So this is our busywait function, and let's calibrate it here to see how long this thing takes here. Okay, so it's clearly not, I'm not delaying long enough. I'm going to try to sort of tune this to make it be approximately, so let's go up here. So here you can see we've at least gotten close to the ballpark when I pass in a 0.8 for the amount of time I want to sleep. We're somewhere in the ballpark of waiting for 0.8 seconds. That's really all I need here. And so now what I'm going to imagine here is that my friend texts me, and if I'm at work, I'm waiting 8 hours, and we'll imagine that this is our equivalent of being at work for 8 hours. And if I'm at the gym, I wait for 1 hour, and this is our equivalent of being at the gym for an hour. And then over the course of my day, I simply go through my day and I first go to work and then I go to the gym, right? And I might do other things too, but those are not going to be logged here by our profiling. Maybe our friend's only going to text us between the hours of 8 and 5 or something like that. So again, I'm recording this X variable here simply so that Julia's compiler doesn't get too smart for us and excise the busy waiting that's going on in these functions here. And so here I can define my days. And now we can run it once to compile it again because compilation takes time. That's a good idea. And now here we'll use Julia's profiling standard library, right? So the profiling library has an internal buffer that you don't typically directly access. You often have to remember to clear it manually though, because it does not clear that automatically when you enter it. That allows you to aggregate runs across different commands, which can occasionally be useful. And so here we're going to imagine running this essentially for 30 days worth of data. It returned a number because of that X variable that we were using to prevent Julia from eliminating the entire loop. And so now what I'm going to do is I'm going to show you what the profile data looks like. And the profile data can be printed in a couple of formats. I'm going to use the flat format here. And what you can see is that there are measures of the line and the amount of time spent. And what you can see here is that, for example, here at work, it got 27 counts in the work, executing the work function, and it got 5 at the gym. Now, keeping in mind, remembering this is not a whole lot of counts, so keeping in mind that that sampling profilers are subject to noise. This is fairly consistent with about an 8-fold difference between them, right? Plus or minus square root of 5 is about 2, so there's quite a large range of variation in terms of this particular time here. Right? So you can view this profile data in text format this way. Another way you can do it is you can see who called whom, and that's in a tree format here. And what you can see here is that my days sometimes calls work. Here from line 4, it calls work. And from line 5, it calls gym. And you can see the step in here, the further steps inside there. And what you can see here again are the actual times and number of snapshots that have been acquired. So the remaining number of calls here, 27 here and 5 here at the gym, for example, right? So this is another way of viewing the same data with a little more informative way, because you can see the actual execution of flow in your code. The other thing that you can do is you can visualize this profile data. And so what we're going to do here is we're going to use a package here called profile view. And I hope you can sort of see this, but what this represents the profiling results as is it's called a flame graph. So in a flame graph, the idea is that these bars here represent individual sites in your code. And the vertical axis represents call depth. So here, for instance, my days calls work, which calls busy wait, which, because we have to do some work to prevent the compiler from eliminating, calls plus, right? Likewise, my days also from a different line calls gym, which calls busy wait, which calls plus, right? So that explains the vertical nesting of bars. The horizontal nesting, the width of a bar is proportional to the amount of time it takes. And one of the rules is that every bar has a width that is at least equal to the sum of all the bars that sit on top of it, meaning all the things that it called, right? So in this particular case, you can see that my days called work, and that accounted for all of the runtime of this line of code, right? And most of the runtime of this line of code, not all of it, because remember, we're adding those X values to keep the compiler from simplifying things too much, was actually on calling busy wait, right? So, and likewise here with Jim also. So you can see that this profiling information is giving you a measure by the width is proportional to how much time each particular line takes, and the call depth is on the vertical axis here. And so we can use performance profiling in order to understand where different lines of code, or where your code is spending its time. And so let's create a simple mathematical function here involving two matrices A and B and a vector X. We're going to create this and run it once. And then what we can do is we can time it, see how long this thing takes. And so here you can say it's about 0.6 of a second or so. And let's profile it. And I'm going to use the at prof view macro here, which is similar to manual profiling, in order to see where it spends its time. Now, I'm not going to go into a lot of the details here, but what you can see is that it's these multiplications, these stars here, which were in our code, are the things that are taking time. And interestingly, if you delved into this in a little more detail, you could learn that it's the matrix multiplication, which is much wider than the matrix vector. There are internal code differences for handling matrix multiplication from matrix vector multiplication. So you might decide on a whim, and we're going to, in the next lecture, we'll actually get into why this works in much greater detail. Let's try reordering the code. So instead of first multiplying the two matrices and then doing a matrix vector multiplication, what if we first multiply the B matrix times the vector and get another vector, and then do the A multiplication? So this is functionally equivalent to your other code up to sort of small issues of round off error. And so we can define this function here, and we're going to time it. And now you can see, wow, this is an awful lot faster, right? So this is a particular case where it's not that our code had type inference problems or anything like that, but we've used profiling to detect that a matrix multiplication was the main bottleneck. And by just a very small arrangement of the code, you can see that we made it much better. And so the final step that I want to show you, though, is that you can also use profiling to detect these type inference problems. And so you may remember that when we this add to function that we created, that it was slow when we passed it a vector of number or a vector of any, right? And we can mimic that again here with the B time. This is the case where it knows what the types are, but in this case here where we pass in an any, then you can see that it's going to be much slower, right? And so, in fact, I guess I did that here on the next line. So, so what we can do instead of just timing it is we can actually do profiling of the execution of this. And again, because this is such a short amount of time, you can't use Julia's standard at profile or the at prof view. So the benchmark tools package very helpfully has an at b profile, just like at b time is the version of at time for fast running code. So too is at b profile is the analog of at profile. And so here, let's profile this running code. Whoops, sorry, I forgot to modify this. Okay, so now it's taking the profile here. And what you can see is it actually produces this interesting looking output here, where it's essentially showing you it's a slightly messed up looking histogram. Let's see if that's just a consequence of how printed. No, it's reliably a little bit messed up, but this is intended to be a histogram of the actual runtime. So the fastest ones were in the ballpark of about 35 nanoseconds or so, but you can see that there were some executions that took over 300 nanoseconds as well. This is a very nice way of measuring the execution time of your code. But what's really nice is that when we visualize this in at prof view, it also adds one extra bit of hints that there's a problem, and that is, you notice now the appearance of these red colored bars near the top. And this red evokes the same red that's used in Cthulhu to show type inference problems. You can see that there are non-red bars sitting on top of them. These are the things that do the actual work. These are the calls that actually carry out the operations of add2. It's what is essentially, but you can see that most of the space above the red bar is empty. What is happening there is behind the scenes, deep in Julia's C code, it's looking up which method is applicable. And that's what that essentially all that missing time is it's that time spent trying to figure out which method is going to be applicable. And so these red bars should be an immediate draw to your eye when you are going about trying to resolve performance problems in your code. If you profile it and you see red bars sitting at the top and they, right at the very top, meaning no other colored bars above them, then you know that you have a performance problem. That performance problem is due to runtime dispatch, and it's something that should be fixed. The profiling libraries and user interfaces actually will color and have another special color, sort of a yellow-orange color, and that tags bars that are doing what's called garbage collection, which is essentially cleaning up no longer used memory. If your code allocates more than it needs to, those yellow bars may also be something that's worth looking at. Okay, so just for reasons of time, I'm going to call it quits here and just summarize. Julia, I think as we've shown, can be fast, but in order to use Julia well, you do have to avoid some common gotchas. And so one of the most common ones that beginners make is to use global variables that Julia can't infer the type of. On the homework, you'll learn to see that. This is, Julia has a very helpful performance tips page in its manual, and this is the #1 item on that page, which is a very, very common gotcha for newcomers. We also saw concrete examples today of the dangers of using containers like arrays that don't have concrete element types, right? So you can do that if your code requires it, and there are genuine circumstances where that's necessary, but anytime you can use containers with concrete element types, it's far and away the best. And it's always very helpful to reason about your code, and often you can figure out what's wrong from that. But in many cases, and especially as things get more complicated, it becomes very helpful to have tools. And so you should measure the time of your code. You should bench, and then if you've got problems, you should profile it and visualize the profiles and try to understand what the causes for slow performance actually are. Okay, and with that, I will call it quits. Thank you for your time and attention, and we will see you in the next lecture.